Think for a second about the absolute sheer volume of data flying through the air and cables all around you right now. Bank transfers, military secrets, your personal messages. The internet as we know it is a total marvel of classical physics. But what if I told you it's about to be completely reinvented by the incredibly weird, counterintuitive science of the subatomic world? Well, welcome to this explainer. Today, we're diving into a transformation so profound, it promises a future of uncrackable cybersecurity, blistering computational speeds, and scientific breakthroughs we can barely even fathom right now. We're looking at the birth of the quantum internet. So here's our roadmap for today. We'll kick things off with the quantum tech revolution and its real-world applications. Then we'll dive right into the vision for the quantum internet, confront the big distance problem, break down exactly how quantum repeaters work, and finally, look at how we're going to build a global network. All right, Section 1, the quantum tech revolution, the race for advantage. To really get the quantum internet, we first have to understand the massive, wider revolution happening right now in quantum information science and technology, or QIST. The big goal here is something called quantum advantage. Basically, that's the moment when quantum systems start performing significantly better than our current classical technologies. And the stakes for getting there first? They are astronomical. Just look at the money involved. According to a McKinsey report, the private sector poured over $8.5 billion into quantum tech in 2024 alone. That's a staggering amount, and governments are moving just as aggressively. The U.S. passed the National Quantum Initiative Act, pumping $1.2 billion into research over 5 years. The United Nations even declared 2025 the International Year of Quantum Science and Technology. So we aren't just talking about some theoretical science experiment anymore. This is a literal global technological arms race. Moving to Section 2, Applications of Quantum Science, Categorizing the Tech. So what exactly is all this investment trying to actually build? Well, QIST really breaks down into 3 main pillars. First up, quantum computing. By using qubits instead of regular bits, these machines tackle impossibly complex calculations like simulating materials at the subatomic level, though, to be fair, early prototypes are currently in the noisy intermediate scale era, meaning they're still pretty prone to errors. Next is quantum sensing. This one's wild. By harnessing the extreme fragility of quantum states, we can measure microscopic disturbances. This is paving the way for next-gen MRIs and advanced stealth detection, and it's actually the most promising near-term tech. And finally, quantum communication. This uses the absolute laws of physics, rather than complex math, to transmit data with totally uncrackable security. Which brings us to Section 3, the quantum internet, connecting all this quantum tech together. This is the ultimate vision. What happens when we take those powerful computers, hyper-accurate sensors, and secure communication lines, and we network them all together over massive distances? We get the quantum internet. But to really appreciate how this network operates, we have to grasp how it handles data, because it is fundamentally different than our current internet. Think about the classical bit. The entire digital age has been built on this. It's binary. It has to be a 1 or a 0, on or off. Pretty straightforward, right? But then we have the qubit. Qubits leverage a crazy property called superposition. Basically, before a qubit is actually measured, it exists in multiple states at once. It can be a 0, a 1, or probabilistically anywhere in between. Because of this, it can encode vastly more information than a standard classical bit. But the real magic of the quantum internet? That relies on this next concept, entanglement. This is a phenomenon where multiple particles become intrinsically linked to each other. If you have 2 entangled particles, the state of one instantly dictates the state of the other, no matter the physical distance between them. They could be across a room or literally across the galaxy. It is delightfully weird, and it happens to be the absolute bedrock of quantum key distribution. Because these particles share this inexplicable link, any attempt by a hacker to intercept or eavesdrop on a transmission immediately disturbs the system, instantly alerting the users. It's an uncrackable shield. On to Section 4, the distance problem, environmental hurdles. Okay, so if entanglement is so incredibly powerful and secure, you might be wondering, why haven't we connected all our quantum computers across the globe yet? Well, the big holdup is distance. Quantum states are devastatingly fragile. As entangled photons travel through fiber optic cables, they hit environmental noise, things like heat, vibrations, electromagnetic radiation. This causes something called decoherence, where the quantum system basically just loses its special properties and collapses into regular classical noise. Plus, photons physically just get lost in the fiber over long distances. And finally, you have the observer effect. The very act of measuring or even looking at a quantum system can disturb it, causing it to collapse into a single state and destroying the data entirely. And that observer effect brings us to a massive, absolute roadblock in physics, the no-cloning theorem. Look, in the classical internet, when a signal gets weak over a long undersea cable, we just use a repeater. The repeater measures the incoming ones and zeros, copies them, and blasts them out at a higher power. Problem solved. But the no-cloning theorem strictly forbids this in quantum mechanics. You literally cannot copy an unknown quantum state. If you try to measure it to repeat it, you destroy it. End of story. So how do we fix that? Section 5. How quantum repeaters work and how they solve these distance issues. How do we get around the fundamental laws of physics to send data globally? The trick is, we don't copy the data. Instead, we manipulate the entanglement. Enter the quantum repeater. Imagine two users, let's call them Alice and Bob, who are separated by vast distances. Instead of using one long, super fragile cable, we break the journey into manageable, shorter segments using quantum repeaters in the middle. So, step 1, these repeaters generate short, point-to-point links, essentially creating a chain of localized entanglement with their immediate neighbors. Now for the ingenious aha moment. How do we actually connect Alice all the way to Bob? The repeaters perform an operation called entanglement swapping. Repeater 1 looks at its link to Alice and its link to repeater 2 and performs a highly specific quantum measurement. By measuring its local links, it indirectly stitches the connection further down the line. It essentially swaps the short-distance links to form a longer chain. And by repeating this swap all the way down the chain, the repeaters are consumed. And what remains is a direct, long-range, entangled connection spanning the entire distance from Alice to Bob. And notice, no data was copied. The no-cloning theorem remains completely unbroken. Now that Alice and Bob share this high-quality entanglement, they can use a process called quantum teleportation to securely transmit the state of a qubit from one end to the other without the physical particle ever having to travel the full distance. It is an absolutely stunning mechanical workaround. Section 6. Building a global network. Real-world deployment. So, now that we have the mechanical blueprint to beat the distance problem, how is this actually going to be deployed in the real world over the next few decades? Well, quantum repeaters aren't a static technology. They're evolving across distinct generations, kind of like cellular networks. Today, we're working with 1G repeaters. They're a bit slow because today's hardware is noisy, so they rely on a process called distillation to purify weak, entangled states into a single, strong one. It works, but the communication rate is definitely limited. As hardware improves, we'll move to 2G repeaters. These will introduce quantum error correction, encoding information into blocks of qubits to mitigate errors and drastically increase bandwidth. And eventually, we'll hit 3G repeaters. These won't even need to do the slow step of entanglement swapping. They'll act much more like today's high-speed internet routers, dynamically correcting errors as the quantum states physically transport from node to node at blazing speeds. And here's the coolest part. This technology won't just live in underground fiber optic cables. The future quantum internet is going to be a massive hybrid web. It'll combine these ground-based repeater nodes with free space lasers fired between terrestrial telescopes, mobile platforms like drones, and even intercontinental satellite links. In fact, real-world deployment has already started. China currently operates a 2,000-kilometer quantum network for government and military use. And European countries and the US are heavily investing in scaling up their own testbed networks right now. This whole shift from our classical internet to a quantum one, it really isn't just an IT upgrade. It is a fundamental shift in how human beings process, secure, and transmit reality itself at the subatomic level. With applications ranging from flawless autonomous vehicle navigation to huge medical breakthroughs and completely impenetrable national security networks, the societal and economic stakes are beyond massive. Which leaves us with one final critical thought to ponder today. As this uncrackable network becomes a reality, who will control the infrastructure? And ultimately, who will hold the keys to this unhackable future? Thank you so much for joining me for this explainer. I really hope this helps you understand the absolutely fascinating quantum world waiting just around the corner.